Hello, today I'll be going over the Bayesian two-sample normal model. First I'll go over some of the theory, and then I'll go over how to implement it in R. This first section here goes over the model setup, right? So we'll have two independent normal samples, the first one with n1 observations, the second with n2. Each one will have their own respective numbered parameters, mu1 and variance 1, and the same for number 2. So for the Bayesian derivations, the best way to do this is by actually altering the variance into the precision. So we say the precision is 1 over the variance. So the model actually looks like this for unknown parameters mu and tau. So we'll have mu as the mean and 1 over tau as the variance for both samples. So to calculate the likelihood, we say that is proportional to this. Okay, so each one of the PDFs, right, is IID, but independent. So we multiply each single one together to get this final product. So it's tau to the n over 2, and then the regular e to this item here that you typically see in the normal distribution. So we have two of these for both samples, the product of both of these. So as with any Bayesian process, we need a prior. So the easiest one to set up is the reference prior. So the problem with this is that it's not a probability density, so it is improper, but it does mimic the frequentist version of this. So to find the posterior using reference prior, in this case improper prior, we simply take the likelihood and multiply it by this prior. So typically for a one sample normal, you'll have 1 over tau, but because we have two samples in this case, we need two 1 over taus, each tau 1 and tau 2. So for the prior, for the posterior, it's proportional to the likelihood times this prior. So we have these this product here down here, except now up here in the integrand it's different, right? So we essentially just break it down into n minus 1 times the sample variance plus n times mu minus y bar squared up here. So the only difference is that we have these two in there, so we essentially just flip this up, so now it's n over 2 minus 1. So now we have the product of these two items as the posterior. Now what we really want to get is the marginals, right? So the marginal in these cases are the same as in the one sample normal model. It's just that we'll have two of each of them. So we'll have two tau 1 given y's, or sorry, two tau given y's for I equals 1 and 2. So it mimics, like I said, the one sample normal model. So what we'll have for tau given y is a gamma, n minus 1 over 2, n minus 1 sample variance over 2. And then for mu given tau and y, we have that follows the normal given y bar mean, 1 over n tau variance. And then instead of this, we can get the marginal of mu specifically without conditioning on tau, and that becomes a t-distribution with n minus 1 degrees of freedom, location y bar, and scale sample SD over square root of n. So again, technically each one of these, there's two distributions for each one of these because we have two independent samples. Now, for independent priors, so a little bit different, but this is what we typically see in practice, right? So proper priors, we say that mu follows a normal given a mean and 1 over b variance, and that's independent from the tau prior, which follows a gamma, c and d rate and scale. Okay, so the same process as before. We multiply the PDFs of these four priors with the previous item we had up here. That we had up here. So it's the likelihood times these priors. So we'll end up with one part of the normal, right, for each one of these. So e to the negative b over 2 mu minus a squared for both I equals 1 and 2. And then we have this from before, And then we'll also have this, right? So this is from the gamma. So essentially it's proportional, right? So we're taking away all the constants that we don't need. So we'll end up with this big PDF here, okay? So to find the conditionals, it's the same exact process again as the one sample normal model, but now we'll have two of each one of these for the two separate independent samples. So tau follows the gamma again, and mu follows the normal. I won't go into this, but it's the exact same result as the one sample. So before we go into R, we need to cover the Gibbs sampler and then how to obtain proper priors. So the Gibbs sampler's Markov chain Monte-Carlo algorithm that essentially has many states, right? So m from 0 to infinity states. So to start off, we want to find a starting point. This can just be any initial starting point that we call mu0 and tau0. These are the two parameters we're estimating. Now, the second step here is essentially if we're in a current arbitrary state of the chain at mu m and tau m, then to obtain the next state, which is mu m plus 1, tau m plus 1, we do this in two steps. So for j equals 1 and 2, for the two independent samples of this problem, we generate tau m plus 1 for both 1 and 2, and then from this gamma distribution. So we know all these different items, including mu m, so that's just from the previous step. So if we're calculating tau 1, then we use mu 0 here. And then after that, we find mu m plus 1 for both j equals 1 and 2. And we simply use the tau m plus 1 in these spots here instead of tau m. So we're really using, a sequential, right? So we know all the other parameters as well. Okay. So that's how you derive the Gibbs sampler in R. Now, to find proper priors for both mu and tau. So the normal prior for mu, we want to ask two questions here. The first one being, what is the best guess for mu? I for 1 and 2. So to answer that question, we asked the best guess. So whatever the best guess is, we set that as a prior mean A. And then the second question we want to ask is what value of mu has a 5% chance of exceeding it. So in terms, that would be probability that mu is less than some value of mu that has a 5% chance of exceeding it, and then you set that equal to 0.95. And then to do the standard normal transformation, we end up with this equation. So from 1, we already know A, and from 2, we already know C, so now we can solve for B here. That way we have both A and B for both mu1 and mu2. Okay, now the gamma prior for tau is a little bit harder to understand, but pretty similar. So again, this follows a gamma C and D rate and scale. So what we can do is we can ask about a percentile of the data. So any percentile, 50th, 60th, whatever it may be. Doesn't have to be 95th. So what we do is we ask for that, and we simply put that here, like we did previously, where C was. So we say probability that mu is less than this random percentile equals 1 minus alpha, and then we solve to get this equation. So the two questions we want to ask: what is the best guess for this percentile? So what's the best guess for the 60th percentile, for example? And then what is the 95th percentile of that percentile? So what value of the 60th percentile, for example, has a 5% chance of exceeding that? So that's where the two questions come from, essentially the same as before, but a little bit worded a little bit differently. So from the previous step, we assume that mu equals A. That's our best guess for mu. And then what we do is we use this equation that we had before. So for instead of mu now, we'll have A. So percentile equals A plus C alpha sigma. So what we do is we solve for sigma from there. and we square both sides to get the variance. Okay. Now, for question 2, let's say that number, the 95th percentile of the percentile, we'll call that p.95. And what we do is we set it up the same way, but now the percentile is going to be over here instead of mu. So we say the probability of the percentile being less than p.95 is 0.95. And then to normalize it, what we do is we set it up exactly like sigma, right? Because we want sigma squared on this side. So we do minus a over z alpha on both sides. So now we end up with probability that sigma is less than this item. And then before we start trying to figure out how to solve that, we take a step back and realize that tau follows a gamma in this case for the prior, which means that sigma squared follows an inverse gamma, right? Because tau equals 1 over sigma squared. So then the mode or best guess in this case with inverse gammas is different. So it would be d over c plus 1. So what we do as the first step to solving it is set the prior mode of sigma squared to our best guess of sigma squared. So the prior mode is d over c plus 1, and then we set that equal to what we had before, which was this, right, our best guess for sigma squared. And then from there, we set up the second equation to solve numerically. And we use exactly what we had before here. So probably that sigma is less than that item, but now we square both sides, set that equal to 0.95. And then we can also change this to tau over here, but we just have to flip this side. Okay. So now we have these two systems of equations, or this system of equations to solve for both C and D numerically in R. Okay. So here's some of the R code that'll set up an example to do this two-sample equation, or posterior, sorry. So what we do here is we source two files. One is the Gibbs Sampler code, and then the other are just supporting functions, as well as the library we need. So the example dataset is going to be corn yields for two different types of fertilizers. So first I'll set up the data frame here and give you a look. So there's two groups, A and B, and then this is the response, I guess, technically. So it's the yield for each one of the two groups of fertilizer. So here's just an initial density plot of the two, and I'll calculate x bar and SD for each one. So so both of the densities are fairly normal in both cases. So this part here is actually finding the priors of mu for group A and B. So this function, all you have to do is supply it with the best guess for the mean of group A, and then the best guess for the 95th percentile of group A, or whatever percentile you'd like. Okay. And then what we can do from there is extract the prior mean and the prior SD and prior precision for group A. And then for group B, we'll do the same exact thing. Okay, so this is finding the prior for sigma or tau for group A and B. So this first normal percentile, the SD, is us setting up the best guess for sigma, the prior mode guess for sigma. Okay, so you provided a mean value and a percentile given whatever p you want, and then this second one is returning the prior percentile guess for sigma. So the percentile guess, not the best guess. So we say it's the same mean as before, but it's just a little bit higher since it's the 95th percentile of the percentile. And this is the main function using the results from here. So, right, so we're providing it the sigma A SD, and then the percentile SD here. So this will return the shape and rate parameter for the gamma distribution of tau. Okay. So we extract those from this data frame. Okay, and we do the same thing for B. Okay, so now is where we get into the simulation using the Gibbs Sampler. So this is a function, a custom function that will take in the number of iterations to burn in how many you want to skip at each time. Then it'll take the priors, and then you'll provide an initial. This is just, you know, any initial, like I said before, and then you provided the data. So now we'll have a simulation of the posterior for both group A and group B. Now here are a couple plots of interest using that said simulation. So we have the marginal posterior for mu for group A and B, and then marginal posterior for sigma for groups A and B. Okay, so the top two are the posterior densities of mu for group A and B. So what we can really see is there's not a huge difference. You know, maybe group A is a little bit you know, heavier on the right side compared to group B, but they're pretty similar. The main difference is with the standard deviation. So we can say, let's see, okay, so 160 versus, you know, 120 or so. So the variation in group A is a bit bigger compared to group B. So that's what we can get out of this. But what we really want to look at is the predictive density for new observations from groups A and B. So what this code does is it takes a number of iterations from the Gibbs Sampler, and then it'll make a data frame to fill up through this for loop. So the for loop for each one of these, each item from this vector, it'll extract a mean from the simulation and then a sigma, and then it'll generate a random normal variable. Okay, and we'll also do that for group B. So now we'll have enough observations to create predictive density for groups A and B. And like we had thought, maybe group B is a little bit larger, but it is tighter than group A. So the HPD interval on the bottom here can show that as well. So for group B, it's tighter compared to group A, but the means are fairly similar, the modes are fairly similar. Thank you for listening.